Yes. I'm playing that.
Okay, don't know what just happened here. That's not great. Okay, somebody asked me about a question. Can you be specific? And I will try to answer it. I mean, can you like tell me what it was asking? All right, page what? 334, 335, number what? 72. Is that the x squared minus 4x squared plus 4? 70, that's the 73 you want to look at?
Oh, 73 and 60.
Okay, just do the first one. Number 73, is it the function is x squared minus 4 over x squared plus 4?
Yes.
Okay. X squared minus 4. And the question said, find any vertical and horizontal asymptotes, right? So I know there's no vertical asymptotes just by looking at the bottom because it doesn't factor. Even if I set it equal to 0 and try to solve, I get x squared equals -4. And when I try to square root it, I get an imaginary number. Also, is there any possible way to make that denominator 0? I mean, just looking at it, I can't because I'm squaring something. The most positive, the closest to a negative I'd get out of that is maybe a 0. And then I add 4 to it, it's positive. So if I can't make the bottom negative, you're not going to have, if I can't make the bottom equal to 0, you're not going to have holes or VA. So there's no VA, but there is a horizontal asymptote. What did we learn about that? If they're equal, you take the coefficient. So my horizontal is y equals 1. And that'll help me on my sketch. Sorry? On 73?
I think so.
Is it my key or the books? I mean, is it my handwriting? Well, we can look.
Why don't you use limits as well?
You can. Yeah, absolutely. It's the limit to infinity or limit to negative infinity. And what are your limit rules? When the power's right. Yeah. But no, I love that you know that. That's great because that's literally the calculus approach. The pre-cal approach is just kind of memorized. But you're really looking at that and going, oh, these are growing at the same rate. If they're growing at the same rate, I use coefficients. So yeah, that's a great way to think about it. It says that? Okay, so that would be a mistake on this, and we know that, right? So 335, number 73. Yeah, I'm just cutting and pasting. That's so terrible. The limit equals 1, so y equals 0. That makes no sense. No, oh, you don't see this. Yeah, they literally solved it. If you look at it, they literally went, oh, the limit is 1, so y is 0. Okay, that's a typo, and that's the third one I found in this book, and we've done very little with it. So that should be so y equals 1. In fact, they even graphed y equals 1 down there in the problem, but that's just a typo, which is unfortunate. But anyway, so yeah, just with a grain of salt, evidently they didn't hire the right people to do their proofing. Because I found one mistake in a problem, and then I found 2 mistakes so far in the solutions. So, but yeah, you can see they did actually graph y equals 1 there as a horizontal. So that's just a mistake there. So, and then the next thing they asked, was find the intervals where f is increasing or decreasing. So again, if it's x squared minus 4 over x squared plus 4, how do I find intervals where it's increasing or decreasing? Right, it increases, a function increases when what? When the slope is positive, decreases when the slope is negative. So I need to find the derivative, which is the slope, right? So the derivative is low d high minus high d low, all of that over the low squared. Now, the goal when you take a derivative, I want to find critical numbers out of all this, right? Because the critical numbers are going to be the breaks where it could possibly change from increasing to decreasing. So the goal is to evidently set this equal to 0 or set this to D and E, right? Well, if I'm trying to set it equal to 0, I'm probably going to want to have it factored, right? So before I go in here and start distributing everything out, couldn't I look at this and factor out a 2x? Wouldn't that maybe be helpful? Rather than distribute it in and get up a something x cubed, right? I could factor out the 2x and I'm left with what? X squared plus 4 minus what? Because think about it, if I pull the 2x's out of there, right? I'm left with this x squared plus 4 minus x squared plus 4, right? As I distribute. That was kind of nice, wasn't it? Now, if you don't see that, FOIL it out, but my x squareds cancel, and I'm just left with 8 times that. And this big thing. So where would the derivative be 0? The derivative is equal to 0 when it's 16x. So therefore, when x is 0. So there's a critical number. And then where else is that equal to 0? The derivative of x is d and e, nowhere. You could say doesn't exist, I guess. There's no place where it doesn't exist, right? Because the only place it would not exist is if the denominator was 0, right? But the denominator is never going to be 0. We just talked about that. So that's your only critical number. So if I'm checking this thing, I've got a critical number at 0. I don't know why I just did that. If I'm checking this thing at 0, I can check the derivative from the left side and the derivative from the right side. If the book says anything different than me, please tell me so I don't continue to build on my error. If I plug a negative in there, what do I get? Sorry, if I plug a negative in there, what do I get? That's the derivative. I get a negative over a guaranteed positive because I'm squaring the bottom, right? So that's a negative. So it's decreasing there, and it'd be increasing on the other side because when I plug a 1 in there, I get a plus over plus. Yes?
On the key, you're finding the, well, I guess that's the next part. But when you're finding the local maximum and local minimum, it said there's a local maximum, but wouldn't it be a local?
Looks like a local min to me.
I think on the key it said.
Here, hold on. It says my critical numbers.
It says f at 0 equals -1, which is a local maximum. There are no local
16x. At -1, it's negative. This is shocking. This is very chaff-like. I mean, it's very obviously. Now, look, they even said it's increasing from 0 to infinity. They said that. It's decreasing from -infinity to 0. But then they said it's increasing to decreasing at 0. No, it's not. It's decreasing to increasing. So they literally said it's increasing here and decreasing there. But again, nobody's proofing their work. This is really disappointing. But the upside is I use my book very little. You will use this very little after these next few chapters. Like, and I mean very, very little. Like my students last year were like, we don't even remember using the textbook. So this may be the end of it. My keys are good because they've been proofed or whatever. Are you with me? So this is definitely a relative min, right? You know that. And then what is the relative min? So really sorry about that. In some ways it's good because it's really questioning what you know, right? I mean, you were kind of thrown by that. You're like, wait a minute, which is good because if you just took it for granted, you probably don't know what you're talking about just yet. So to find out what that value is, I would plug the 0 back in here and get what? -1. So my relative min is actually -1. It's not a point, right? It's -1. And then the next questions were, so I didn't specify the intervals, but the book was correct on that, right? At least, but they just got the local max min stuff. It says find the intervals on which f is concave up or concave down. So how do I do that? I got to find the derivative of the derivative, the second derivative. So the second derivative, I'm going to go back to this simplified part and say low d high is 16 minus high d low is 2 blah to the first times 2x. Well, that's kind of a mouthful. Over the low squared, which makes that now the fourth. Okay, so this is pretty terrible looking. So what would I do here? I would probably try to factor this as much as I could because I'm trying to set it equal to 0, right? And I can see that I can take out a 16 and I can take out one of these x squared plus 4s. So if I take out a 16 and an x squared plus 4 out of this big thing, and you could visually now just kind of get rid of that, and that. What do I have left? An x squared plus 4 minus a what? 4x squared. You seeing that? Yes, no? I can tell you right now, this doesn't feel a lot like a test question. It feels a lot like a test question from like 1970 when AP really beat you over the head with the algebra. You're not going to feel this on my test. You're going to have to go through these processes, but you're not going to feel this much labor. And honestly, even on the AP test, they don't do this to you typically. So now that I've got it kind of cleaned up, right here, I could even cancel one of these out if I want to. You see that? I could really do that if I wanted, but even if I didn't, I could leave it. And this gives me a 4 minus 3x squared on the top over that. Let me see if they have something similar.
They do, they just canceled out the.
And they did cancel out. So you don't have to, because again, it's not going to give you any zeros, right? And it's still, even if it did, like even if that was x squared, like say that was x squared minus 4, x squared minus 4. And that was the original problem. You would look at it and go, wait a minute, even though it gave me a 0, those zeros would not be in the domain. So I'd end up throwing them out anyway. So if you want to cancel something like that with this, and now you just have 3 of them, totally fine. So now that I have my second derivative, where is my second derivative equal to 0? Well, when the top is 0. Or the bottom, but the bottom can't equal 0, can it? So I would be really clear. I would say, okay, the second derivative, which I said right here, it's a big long equal sign. So I can say equals 0 when the top is 0. So when is that? If I'm looking at the top equal to 0, I could divide away the 16. It doesn't do anything, right? It doesn't have a variable with it. And then I could set this part equal to 0, and I get 4 equals 3x squared. X squared equals 4/3. And what happens when I square root both sides? Plus or minus 2 over root 3. Now, ballpark me. What is 2 over root 3 going to give me? Root 3 is about what? 1.7-ish? What's 2 over 1.7? Just a little bit bigger than 1, right? So when you go to do your number line analysis on this, if that's 0, I'm just going to mark my 2 over root 3 like it was a 1, negative 2 over root 3. And I'm going to use those to check my second derivatives. But as long as you know that means just a little bit bigger than 1, check the second derivative to the left of a little bit smaller than 1, right? So maybe -2. Maybe check the second derivative at 0. Maybe check the second derivative at 2. You can check it at 1 on the inside also, but I'm a fan of 0. So what happens if I go to the second derivative and I plug a 0 in there? I get 16 times what? So positive on the top. What about the bottom? Anything, well, it's cubed now, but because that's squared, it's going to make that part positive. When you add a 4, it's still positive. So yeah, the bottom's going to be positive too. So right there, if I check 0, it's definitely going to give me a positive. So that means what? Second derivative, concave up. So I usually do that for concave up. Don't put increasing because that's for first derivative, right? So I know the concavity is positive. And if I check -2 in there, what's a -2 squared? Positive. What's 4 minus 3? I'm sorry. If I plug a -2 squared in there, it's 4, positive 4. Then I get 4 minus 12, which is negative. And the bottom's still going to be positive. So I get a negative or positive, which is, so concave down. And when I check 2, I get 4 minus 12, which is also negative, right? And negative over positive is also concave down. So what does that make the points here? What does it make those? Inflection points or points of inflection. Why?
Because it's changing.
Because you change concavity there. And whenever I have a change in concavity, then you have an inflection point, right? And whenever I have a change in increasing and decreasing, I have a relative max or min, right? Okay, so I've got that. Now, remember when I asked you, what are my critical numbers, you would say 0. If I ask you, what are my inflection points, don't say -2/√3 and +2/√3 because those aren't points. Points have coordinates. Critical numbers are just x values. So even though they're kind of finding them the same way, right? You're looking at first derivative to find critical numbers. You're looking at second derivative right here to find inflection points. When you write them on your test, make sure inflection points are actually points, which are annoying because these are really ugly values, but I try to avoid that stuff. So if I plug that back in for x, what do I get when I square it? That right there gives me what? 4/3 when I square it. What's 4/3 times 3?
4.
4, and 4 minus 4 is?
0.
So, sorry. When I plug that into my original function, sorry, I want to find the point. I get what? When I square a 2/√3? 4/3. So I get a 4/3 minus 4 over a 4/3 plus 4. Now you can actually do the math on that and find common denominators, but you remember my little trick I like to use? Anybody?
Multiply by 3.
I multiply the top and the bottom all the way through by a 3, which you can do because 3/3 is 1. I get 4 minus 12 over 4 plus 12, which is -8/16, which is -1/2. So it turns out my inflection points are that comma -1/2 and that comma -1/2. Because it doesn't matter which, if I plug them in there, I'm squaring them, I get the same value. You with me? So far, so good. And then that's intervals concave up. So my intervals where it's concave up, I'd say from -infinity to here, it's concave down. From here to here, it's concave up. From there to there, it's concave down. And I would write them in interval notation or with inequalities. I mean, with greater than or less than signs. And stop me at any point. And it says now sketch the graph. So to sketch the graph, I want to give me there. To sketch the graph, okay, I got to put all this together. So ideally, I'd be able to sketch it below, but like to put all this together, right? I'm going to go, well, I know I have a horizontal asymptote at what? Y = 1. I've got a relative min at 0, -1. So I know I have a point right there. There's my real. Wow, you're really annoying. At 0, -1, I have a relative min. I know I have inflection points at about, we said -2 over root 3 was like -1 point something. So at like -1 point something, man, and +1 point something, it changes inflection. And I know that I am from here to there, I am what? Concave down. Now, so if I'm following this asymptote, which I have to do horizontals, right? So if I'm coming in, I got to be concave downward and what? Decreasing. You with me? So I'm going to be decreasing all the way until I hit the y-axis, but I'm going to be only concave down until I hit that. And I know that this point is at -1/2. So actually, I'm going to get rid of these because I can't see what that is. So it changes inflection right there. And it changes inflection right there. So here we go. Concave down and decreasing to there. And then what happens? I'm still what? Still decreasing, but then it switches to concave up. So concave up, but I got to hit that min until I hit this. And notice I'm concave up, but right here, then what do I begin doing? Increasing. So I'm increasing in concave up until I hit that inflection point. Wow, that is really sensitive today.
You see Mr. Hurry is trying to teach.
Yes. And then what happens? Now it switches to concave down, right? But increasing. So I'm going to be increasing, but concave down to there. Now, it would have been really great if I had these little number lines done above my curve, because check it out. If I would have done this, all right, I'm decreasing there, then increasing, and then I'm concave down, then I'm concave up, and I'm concave down. I could have said, okay, decreasing, concave down until I hit that inflection point. Then decreasing concave up till I hit the min, the relative min. Then increasing concave up till I hit that inflection point. Then still increasing but concave down, increasing but concave down the rest of the way. And you can kind of bring this information down into your graph. And if I would have found x-intercepts, I could have found, oh, not only that, but it crosses at 2 and at -2. X-intercepts would have helped me too. I just don't think they asked for it. Are y'all seeing that? We're going to do more of that today. That's why we're trying to put it all together. Yes.
So when you're saying increasing and decreasing, is that the slope or the y values? Because the slope shifts.
Increasing and decreasing, the function is decreasing because the slopes were negative. The function decreases. The function is increasing because the slopes were positive. So you can see right here, this function decreases because the slopes were negative on that interval. And you can see it is decreasing.
Not because the slopes values were increasing, because at the inflection point, it hits 0. Like,
yeah, these, I'm going somewhere, this is like 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, 0, -0.1, -0.2. These are decreasing y values until I hit there.
okay, so now it slopes.
And now, so decreasing y values, or the decreasing y values means the function decreases.
Not the slopes. Okay, that's all.
The slopes aren't decreasing. Well, the slopes are going right here. They're becoming like, it's close to 0 here, and then maybe -0.5 and maybe -1. But that's happening right there because of the concavity.
Okay.
But then the slopes start increasing here, right?
Yeah, that sounds right.
Because you remember that little thing we did? We said if f increases, right? We said its derivative is greater than 0. And we said if the derivative increases, the second derivative is greater than 0, which means the function is concave up. So right here where it's concave up, the slopes are actually getting bigger. But where it's concave down, the slopes are getting smaller. So even though the slopes are getting smaller, which they are, right? More and more negative right there. So when f is concave down, the slopes are decreasing, getting smaller, but the second derivative is less than 0. Yes?
So when it's telling you to just look at a graph and find like where it goes from,
Can't say it.
where f goes from concave down to concave up, how are you supposed to know exactly like?
It'd be tough. Like you'd be eyeballing it. Yeah.
What I did on mine.
But yeah, I mean, like you might pick that, and somebody else might go, I thought it switched there. You just do the best you can. Usually, what I do is I'll have a graph, and I'll have a bunch of things labeled A, B, C, D. So it's kind of obvious, like there'll only be one choice. But I'm fairly flexible. And if I miss something, and you go, hey, Mr. Hurry, I was thinking about it right there. I'm a reasonable person. Which if you know me well, you know that. If you don't, you'll get to know that. So I'm not going to look at that and go, yeah. So if you pick this and I pick that, whatever. Well, we get it. I get it. So, but yeah, it is kind of a eyeballing if I just gave you a picture. Now, there's a lot going on there. I do a much better job on my test of not giving you something where one small mistake will just destroy you and suck your soul away. I don't do that. So to give you a vision of that, let's look at this right here. So this is a lot of the way you will see stuff on your test. Okay. So for instance, I will give you information like this and say, and I'm on page maybe 129. Is that right? Okay. So page 129, I'll give you the function and I'll give you the first and the second derivative. So you don't even have to do that. In case you either A, stink at doing derivatives, or B, if you make a careless error, right? If you go 2 times 3 is 9x, well, you just got killed on this problem because everything is going to be a disaster, right? So I will give you that, and all you have to do is use it. So let's take a look at this. I got f prime. What do you think I want to do with this if I want to try to sketch this graph ultimately?
Find the points.
Yeah, I need to find stuff like relative maxes, mins, increasing, decreasing, all this stuff, right? And you'll notice when I'm going to graph this, I line up my number line analysis directly with the numbers on my graph. So I can literally take this information and just kind of bring it down into the graph. Are you following me? So check it out. First, function. What can I get out of that? Well, maybe an x-intercept, but that doesn't factor very well. So I gave them to you. So I'm going to go ahead and mark these. Negative, looks like a little bit shy of -1. Okay, so a little bit shy of -1. 1.347, so maybe 1.3 and 2.5. So those are the x-intercepts of this graph. That was a gift because that doesn't factor well. But f prime does. So I can factor that. I can factor a 3x out, and I'm left with x minus 2. There's no place where it's, the derivative is undefined. So I write equals 0, so the AP reader will know what I'm talking about. And what critical numbers do I get from that? So my critical numbers, and numbers are numbers, they're x values, are 0 and 2. So I'm going to mark 0 and 2 on my little analysis here. All right, so I want to check what the derivatives, I'm going to check the derivative at -1, the derivative at 1, and the derivative at 3, and see where the derivative is positive or negative, because that talks about increasing, decreasing on the function. So if I plug a -1 into the derivative, I get a what? A negative times a negative, which is a positive. So this would be a positive derivative, which means an increasing function. I plug 1 into the derivative, positive, negative. A negative derivative tells me decreasing function. And I plug a 3 in there, I get 9 times 1 is positive. A positive derivative tells me increasing function. And from this, my first derivative test tells me what?
I don't know what the first derivative test is.
What's the first derivative test?
It's increasing.
If a derivative changes from positive to negative, At a critical number, there's a relative max. So I know that there's a relative max here, but what is the relative max? It's not 0, it's plug a 0 in and you get a 3. So I know that at the point 0, 3, there's a relative max. So 0, 3, I mark my relative max. I also know the first derivative test tells me what?
Minimum.
There's a relative min where?
At 2.
Why?
Because it's going from
You
decreasing.
keep saying it. I'm so
The
confused.
function.
There's the first derivative. There's the second derivative. There's a function. Why is there a relative min at 2? Because the first derivative switched from negative to positive. Now you can say because the function goes from negative to, went from decreasing to increasing. That's true, but why did you know that? You certainly didn't know that from looking at the picture that I didn't give you. So it was all about the derivative. So say why you know that, if they ask you that. So I know that there's a relative min here because the derivative changed from negative to positive there. And what is the relative min? It's not 2. 8 minus 12, negative 4 plus 3 is negative 1. So the relative min is negative 1. So I can go to the point 2, negative 1 and mark the relative min.
Getting to the point where every time I'm bubbling in a point, I expect that thing to pop up.
Yeah, it's a little annoying. All right, so I have now the relative min. Now remember, don't put relative min as points. A relative min, relative max, a max min, they're always y values. But I'm going to mark the point because I want to know what this thing looks like. Now, right now, you could probably sketch this graph pretty decently, right? You could come in here right now and go, look, it crosses there, it hits there, it crosses there, hits there, crosses there, and takes off. But let's bring in all the concavity too, and then we'll know exactly where it switches concavity from concave down to concave up, things like that. All right, now, so how do I talk about concavity? Second derivative, I've already done that, so I factor it, and I get x minus 1. So a lot of people make the mistake of going, oh, at 6 and 1, I have possible inflection points, but there's no variable at that 6. Ignore that. So what is 1 again? This is where the second derivative was 0 at 1, but what is that? What is that? It's a possible point of inflection or inflection point. We don't know if it is, because to be an inflection point, what would have to happen? It would have to change concavity. We haven't checked that yet. So I'm going to go ahead and mark 1 though, and then check at 1. I'm going to check the second derivative at, say, 0, the second derivative at 2, and see what's happening. What happens if I plug a 0 in that? I get a negative 6 either way, right? So that's what? Concave down on that interval. And if I plug a 2 in there, I get a positive 6, and positive would mean I'm concave up on that interval. And clearly you can see there was a change of inflection. Therefore, you know there is an inflection point, but don't tell me the inflection point is 1. A point is a point, right? So the inflection point, here, I don't have to write that. The IP inflection point is the point 1, comma, plug a 1 in, 1 minus 3 plus 3, 1, 1. So I go to 1, 1, and that is a point of inflection, right? So I'm going to write IP there, or POI, whatever. So I've got relative max, I've got relative min, I've got my x-intercepts. I bet I can do a decent graph. Now watch me flow from left to right. So as I'm looking from left to right, what should it be doing right here? Increasing and concave downward. Now you know what a polynomial looks like, right? You know this is diving, but check it out. All the way through 0, 0 is the first place where that changes, right? Because at 0, all of a sudden it starts going decreasing. So all the way from negative infinity up to the 0, I am increasing, but concave down. Y'all see that? And I'm able to sketch a pretty decent graph. Now, what happens at that point? it's still concave down, but now it's decreasing. And it will continue with that pattern until what? Until 1, where the concavity changes. So until I hit 1, I am decreasing and concave down. Now, what happens at 1? Still decreasing, but concave up. So I'm still decreasing, but I am concave up, and I'm going to do that until what? Until I hit 2. At 2, what happens? Now I'm increasing, but still concave up, and that's going to happen for what? For all eternity? So increasing and concave up. And you just drew a really nice graph. And even if you didn't have the x-intercepts, your graph would have still been decent. The only thing is you might not have crossed there, and you might not have crossed there because you might have come too wide, or you might have gone out too far. But you probably would have hit that really close, right? Because you didn't have any options. If you can find them, yeah, factor them and find them. But if you can't factor it, I'd probably give them to you. All right, let's move on.
Do you want us to mark also with like the relative?
Only do what they tell you. Like I marked them, but they didn't tell you to mark them, all right? Just, you want to plot those, of course. What the heck? Clearly, yours does not look that way.
It said something about insignificant.
So annoying. What page is that?
129.
All right, there we go. I doubt
What's the name of that kid who said that checking his solutions was the new thing?
Show us on.
Do you think he went into making all the solutions for textbooks?
He didn't make a lot of errors.
Joke. I just put it out there.
It's possible, yeah. If he has not been beaten down, and who knows? He was a very unpleasant little fellow. Funny thing about Show, he on Pi Day once, he came to me really excited. He's like, "I'm gonna make my family famous recipe pudding," and I'm like, "Knock yourself out, buddy." And I always tell people, Pi Day, little bite-sized things are probably the best things. Stuff that you got to like get a bowl of or a slice of tend to not be as used. Whatever, knock yourself out. He comes in with this big Pyrex dish of this pie, and it was not right. Like it was rottenish. And I was like, "Oh my gosh!" And he goes, it was like third period or something. He goes, "Hey, I'll make you a bowl." And I was like, "Oh, sure, I've been eating all morning. I'm so full." I'm like, "Oh my God." And well, there's this kid named Billy Kaufman who might live in Homewood because I've seen him around, and it's been a long time. Billy was one of the most kind humans ever. Class president. I mean, just a sweet human being. Super nice. Show piles up a bowl and walks right up to Billy and hands it to him. And I was standing behind him, and I was like, and Billy ate that whole bowl. It was foul smell. It was like rotten eggs were in there. And he was like, "Thanks, Show." I ran into him at like, what's the yogurt place over there by TCB1? Yeah. And I ran into him, and I was like, "Oh my gosh, Billy Kaufman." I was like, "I've told this story about you for years." He goes, "Oh, I remember that." he was like, "That was a rough rest of the day." Like it tore him. I'm amazed he didn't get food poisoning. Nobody touched it, but Show. I guess he built up an immunity. But, good night. It was not good. All right, right here, guys. Not only do I have the function, the first derivative, the second derivative, but I factored it for you, right? So let's just see if we can go quickly here. Clearly, what is the x-intercept? I didn't have to give them to you because it was already factored nicely. You can see that at 2, the y is 0. So I could go ahead and mark right there the point. I can mark the point 2, 0. So I'll do that because that's the x-intercept. And if you're wondering, what about that? Can e to the 3x, which is an important thing, can that ever equal 0? No, because first of all, it's exponential, right? Never hits the x-axis. But also, if you really think about it, positive numbers give you bigger values. Negative numbers just give you fractions. And 0 in there gives you 1. So there's no way that can give you 0, which is important because when it comes to setting these all equal to 0, whether it's intercepts or critical numbers or possible inflection points, these three things aren't going to matter to you. Are you with me? And that's true with any exponential function. So right here, I do have one x-intercept. Right here, you can see I have one critical number at what? If I set that equals 0. 5/3. Go ahead and set it equal to 0. Move the 3x, divide by 3, 5/3. So 1 2/3. So at 1 2/3, there's a critical number. Well, let me check my derivative at 1 and my derivative at 2. And if I plug a 1 in there, what does e to the 3 give me? Aren't these always going to be positive?
Number.
Yeah, they're positive, right? E to anything is a positive number. It can't be negative. It's not below. It's an exponential function. So that's going to be positive. And if I plug a 1 in there, that's going to be a 1 in there, that's going to be positive. So I know that this is increasing. And then if I plug a 2 in there, it's still going to be positive, but the second one's going to be negative. Plus times minus. It's decreasing. So I know this function increases and then decreases. So this must be a what? A relative max, as long as it's in the domain, which it is. And I need to find out what that relative max is. So I plug 5/3 back in there. Now, what is e to the 3 times 5/3? E to the 5th. And what is 2 minus a 5/3? 6/3 minus 5/3, 1/3. So I end up with 1/3 of e to the 5th. So on 1/3 of e to the 5th, I would probably, on a problem like this, have told you what e to the 5th is, which is not a small number. It's probably pretty big. That's why my units are big. So I would have probably told you that. I would have given you that information somehow, because if you don't have a calculator, what are you going to do? And it's 148, and when I divide it by 3, it's roughly 49.47. So let's just call it roughly 50. So my actual relative max would have been 49.47-ish. Let's be APCalc like 3 decimals. But if I'm going to plot 49.5 on this graph, I'm going to go to 5/3, which is roughly what, right here. And I'm going to go up to just shy of 50. So there's my relative max. Are you with me? Because that's 50. Pretty close. And then for the second derivative, where does the second derivative have a possible inflection point? At 4/3, because again, this can't be 0. So at 4/3, so 4/3 is like 1 1/3. So I marked that 4/3, just like right here. I could have marked that 5/3. Okay, and then I got to check the concavity. So I'm going to check the second derivative maybe at 1 and the second derivative at 2. If I plug a 1 into the second derivative, what do I get here? E to the 3 is positive, but then when I multiply it by a -3, it's negative. And when I plug a 1 in there, it's negative. So 2 negatives give me a positive. So this would be concave up to there. And then on the next one, if I plug a 2 in there, e to the 6 is positive. But when I multiply by -3, it's negative. And 6 minus 4 is positive. Negative times positive is negative. So this is going to be concave down here. So what's happening here? Based on what I have here, I have, and this is a point of inflection, right? And that point of inflection, I'd have to plug a 4/3 in there, which gives me e to the 3 times 4/3, which is e to the 4th. And that gives me a what? 6/3 minus 4/3 is 2/3. So it's 2/3 times e to the 4th. We would have to have a way to find that. You're not going to have to worry about situations like this. So just be comfortable with the fact that you will have enough. 36.399. So my inflection point is right there. My inflection point is, what did I say? 36.399. So right there at 4/3, which is 1 1/3, I'm at 36.399. So what is this saying? It's saying, and by the way, this is an arrow, not a concave down. Okay, this is a concave up. So this says that I'm concave up and increasing until I hit what? Right there. So concave up and increasing. Now, let me ask you a question. Isn't that the only x-intercept? So if I am concave up and increasing, as I'm coming this way, concave up, I got to be increasing, but I cannot cross the x-axis again. What do you think's happening? I bet there's a horizontal asymptote somewhere. And my guess is the horizontal asymptote is at 0. Because if you really think about it, if I go to infinity if I go to negative infinity there, you plug that in there, that becomes a positive, and that becomes a really tiny number. So it goes to 0. If you did a limit to negative infinity.
And it wouldn't do back up because you don't have another relative, right?
I do not have a relative min. Yeah. So it might help finding the y-intercept. If I plug in a 0 for x, I could find the y-intercept, which is actually 2 times, I guess it hits right here at 2. Probably should have done that. I found the y-intercept crosses here at 2. That would have been actually really helpful. Crosses here, and then just flattens out. Now, what about next? Then what happens? And really, it's a very short little trip right here between 4/3 and 5/3. Concave down, but what? Increasing. So concave down, but increasing. And then at 5/3, what happens? And that's for the rest of the time, it does what? It's still concave down, but decreasing. Concave down.
Like a straight shot.
Wait a minute.
That's right.
Oh, yeah, and it's got to go through that point. Sorry. So it's got to go concave down and decreasing, but cross through this. Now, it's not a VA, but it almost seems like it. This thing's going to continue probably to move to the right because I can still plug in bigger values. But now pause in a moment. You just graphed this. Now, I know, like in the whole scheme of life, that might not be overly impressive. But if a couple seconds ago, if I said graph this, I mean, you literally just graphed a very nasty equation that I would have had no thought on what it did. And you just used calculus to graph this crazy looking thing on your own. It's amazing. How much time do I have? Not much. 2 minutes? Okay. You talk too much. That first problem didn't hurt. See what you can do. That's all I can say. My goal is to have your test on Friday, but if I can, I can't. Okay, I'm not going to kill myself. But we're like 2 weeks ahead of last year, and we had a 1.2 points higher than the national average on our AP test. So. No, just hey, do things that resemble what we just did. Like we haven't put all of this together. Although if you really think about doing this, I'm basically giving you information as opposed to you finding it. So guys, if you take this information and just like set it up like you would normally, like draw a couple lines and set up this information, you might be able to plug it all in there and figure it out. But at least go through there and see, like, if you see something like this, you could do number 5. We just talked about how to do stuff like 5. The toolbox review, I think I had you turning in today.
No, turning tomorrow.
Turning in tomorrow? That's just information like that you should probably know at this point. Okay. So yeah, definitely look through that toolbox review. You're supposed to, I think, get started on it maybe last night, finish up tonight. But that's just information like, hey, what does it mean if this is this? Or what is this? Or whatever. It's just kind of making sure that you understand what these concepts are. But yeah, do the toolbox review. Take a look at these things, the things that you can do. These kind of questions, I think I have this for tomorrow, don't I? The in-class review is tomorrow. So see what you can do, and we'll pick up the pieces tomorrow.
Do we have like, any like specific show steps?
I can't hear you. I'm so deaf here.
We need to like send the any specific definitions or like have like write down.
I rarely have you write down stuff. It's more like, tell me if this is what's wrong about this definition, or tell me match what this means, or what would the. Or I give you the definition of a theorem, and I go, which theorem is this?
I know I know what it is, just can't put the like I just can't put the words together.
But I might say something like, "Hey, Rolle's theorem says this," and it might be false or true. There might be one small part about it. So if you don't know like all the checks for Rolle's theorem, I might sneak by.
So what we did today was kind of like a combination. Before.
Yeah, putting it all together.
So if you understand that.
I would. Well,
I might
hopefully, yeah.
After school, I feel like I'm like missing something.
No, if you feel really good about what we did today, you're probably in a pretty decent space. But do that toolbox review. It checks a lot of theorems and junk. And
I get a cup and a straw. I will
Yes.
pay you 50 cents.
I mean, like, do you think
I don't have any way to. Yeah.
you think we're like gonna get the test, do the test on Friday, or like,
I feel like we can probably get there because we're not doing anything new.
or
We just spent so long on that first problem, which is not a bad thing. But I probably should have just said, hey, let's just do what we have, because what we had was pretty similar.
Yeah, also just necessary.
Dave,
I know I didn't finish the homework, but like I'm still doing the homework. Just so you don't think I'm like not.
make sure I get it, because you're losing 5 points if I don't get it.
Yeah, I know.
That adds up.
I know. I'm trying to get better at it. I'm losing right now.
All right. That's tough. Out of the system or in?
No. Still in the school system, just like.
Yeah, I know that's,
I'm still doing
it's
it.
turbulent. Well, even if you
Yeah.
just give me what you have, I mean,
Okay.
that can be positive.
Hopefully something.
I'm always here. Yeah, there was something, one of the problems in the key was massively wrong. It was number 75.
You want me to put it in?
Check into that VIT.
Oh, mine's Monday, so like that. But like,
Good day.
I know, this one's Monday. I have to go and I do that another time.
It was kind of fun because when I went around, you would see the other groups. It'd be a group of like 20 people, and they're like, and then you would just cruise right up in front of them in the golf cart, hop out. They would meet like with some assistant, and you would meet with the dean, one-on-one. It was really was pretty cool. I think you got to have a 33 to be a VIT. Even if you know you're not going golf, if you have a 33 or better, and you've got to take advantage of it. It's called Very Important Tiger. And they did it for years, but they shut it down in COVID. So they didn't do it last year, the year before, but basically, if you have a 33 or better, they used to send letters out to you to invite you to sign up. But you basically can go and sign up for a one-on-one day, and they put you with like one of the admissions counselors, and they basically bring you, like, if you want to go into engineering, say mechanical engineering, you'll go meet with the dean of mechanical engineering, or maybe the dean of engineering, and you'll sit down and they'll say, hey, this is what we have to offer, and they recruit you like you're like a star football player. And they drive you around in the little Auburn University golf cart. Like, it was really windy and cold that day. They had the little screens on the golf cart to keep us warm. And we got to cruise around and just hop from place to place. And then you would see like the large groups touring. And you were like, ugh, you're beneath me. But it really was kind of like being a star athlete and getting wined and dined. And then they take you to the conference center and feed you, on their tab. So they fed me. My son and I and my wife went. And then Caroline's appointment was like March 27th. And then they shut down the schools on Pi Day on March 14th. So they canceled all the VIT trips. So she didn't get hers. But yeah, if you have a 33 or better, and you're even thinking about it, go do it. It's a pretty fun day. I thought. But anyway. So how'd that homework go? I'll get to number 75.